So this is, I guess, second one. Call it the kickoff for second project for power monitoring. This one was born of another minor annoyance also. On Linux, or when you're running Linux on a laptop, typically the battery life is pretty poor. It was that way when hadn't even graduated high school yet. In second quarter 2021, it still do be like that. And I mean, it's better, but it's not great compared to Windows. Windows will last, 6 hours standby. I've had Linux laptops only last 2 or less, like 45 minutes, even when you put them to sleep. Or so they say they are asleep. They're not. And there's some tools you can use to troubleshoot this. I mean, the biggest issue is obviously the drivers are not set up right. They're not putting all of the hardware to sleep. But there's some stupid stuff you can catch. The tool is called PowerTop. It tells you the top resource usage for power. The first program was just top, and it told you CPU and I/O disk usage statistics. So I don't see, but it only works when you're on a battery. I have only ever seen it work when you're on a battery. Part of that is there's a battery subsystem and a protocol specification for it that uses SM bus, which is how your computer actually, I mean, you've probably looked at a laptop battery and noticed that there's more than just 2 pins on there, right? I mean, you're talking to it. That's how it is talking to it. So if you get on a Linux computer and you run the I2C dump command, you might see one in the hexadecimal tens, I think, OX16. The I2C numbers are actually cut into families for that. And it reports the power, reports state of charge. It reports a lot of cool stuff, actually. You end up getting a lot out of it. It'll give you battery health. It'll give you number of discharge cycles. You can even ask it, like if I discharge at this rate, how long are you going to discharge? Why would you do that? Well, the battery might be implementing a more complicated wear leveling thing. It might be reading from the cells directly. And it might be, I kind of doubt they're doing this right now, but you could be processing so much data on device you couldn't transmit it back over I2C. So you can also see how fast you're charging, blah, 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 blah. They don't instrument the offline power consumption. That's what I'm going to fix. There's 2 systems that I'm going to design. First, the more practical one, it's just going to be a microcontroller sitting in front of 2 devices. The battery gas gauge as they currently exist, and the Texas Instruments INA 260, which does DC load monitoring. And depending on how you set it up, there's also going to be some minor circuitry to handle the offline supply and that kind of thing. I mean, depending on how you set it up, you only need the INA, but to get PAX UL listed, you need protection mechanisms. You need protection mechanisms on the charger. So I'm just going to use both for now. Midway through the design, maybe I throw one out. I can't throw one out. That's what I was just saying. Midway through the design, maybe I just focus on getting statistics from the INA 260. I might kind of disregard the BQ 4050. The discharge and state of charge stuff, that's going to be, but so, there's a lot of complexity in that. And so this is the first design. It's just going to be mostly software translation. The microcontroller sitting above those 2 devices, you ask it, it sees what you're doing, and it talks to the right one to get the information back. The second design is going to be discretized, and that is less practical. I mean, a lot less practical, because these devices are really high integration. That INA 260 and the BQ, they have built-in trimmed resistors onto the die. So you save a lot of space when you use them. Each one, I think, in singles is about $1. I mean, that might be the 10K price, but it's not really that much worse for. Okay, the INA is 230. The BQ 4050, I'm pretty sure, is like $1. So you're not spending a lot, you're saving a lot of space. The discrete one's interesting because you actually end up making some of the battery monitoring, the cell chemistry monitoring algorithms. It's also better, I guess, from a supply chain side. I mean, that's really hard to justify in my opinion, but technically, and it's open hardware, so you could pick, like, kind of the dream for open hardware is you pick like what is the new one? RISC-V. Yeah, you pick a RISC-V processor. They're not very advanced, you try to make everything Jelly Bean components so that you can get them anywhere. Slight tangent. Oh, but then it's also one of the other interesting things you can do when you make it discrete is you can have far higher bandwidth on the power monitoring. So depending on where you put it, this may or may not help you so much. If it's a typical ATX style supply and you're measuring all that through it, which we're talking about battery switchover, so probably not. But you might not be able to see some of the peak current related to interrupt usage. You could investigate side channel attacks with cryptography using this. You could probably see the sleep states also. I mean, that would be really cool. So that's one of the bigger reasons to follow up on that. There's also some software aside to explore that might happen in the first section. The difference between I2C and SMBus, I mean, it's like square rectangle type deal, but there's a lot of weird quirks that you see when you are talking about SMBus devices, even just I2C. It's pretty bad. I mean, there's devices you can't put on the same bus, even though they say they both support SMBus or they both support I2C. One of the more interesting things, just to say it, a lot of people that when they talk to devices, they don't send the start and stop bits properly. Some of these devices are real sticklers for that. And so basically all that looks like is if you look at two waveforms, clock, data, the clock is the easiest to see. You'll see a trough, right, every time you clock out the data. If you are not doing continued frames, you'll see a whole bunch of individual troughs. And for most devices, that works fine. If you do it properly, though, you see kind of like they bleed together. And so you just have one big trough. This is technically, I mean, I2C devices do not initiate communication, so it's kind of irrelevant. But you do prevent other devices from thinking the bus is open. I don't know why they care. They do. And so, if you're going to do that kind of stuff, like SMBus has some just weird hard-coded limitations in it, and getting the SBS protocol to work over things that aren't I2C. I mean, you just, like, a way to get I2C to just be a serial stream. So, like, you're not in there calling I2C SMBus read block or something. You have some layer where you're probably going to have to give it an address, but you just start streaming data back and forth. That's probably a whole, side project, but it'd be pretty interesting. So this will be cool. I mean, not very glamorous. And then of course there's adapting it to like a full size ATX supply, monitoring the rails off of that.